Okay, so in this video, we're going to be looking at vector spaces and subspaces. And primarily, we're going to be looking at whether a subset of a vector space is a subspace. Now, a vector space is a set of elements that obeys the properties of vector addition and scalar multiplication, the same ones that our traditional vectors in Rn also obey. And a subspace is a set of elements in a vector space that within that set also obeys the properties of vector addition and scalar multiplication. Now, in vector, in the sense of the term vector here, we essentially mean any object that satisfies the properties of vectors. So this could mean that they are functions or other kinds of objects, as long as they meet all of our conditions for vectors. So the properties that vectors in Rn satisfy are these ones listed here. And any set of objects that satisfies these conditions should also be considered a vector space. So for instance, if I add two vectors together, it exists in the space. So let's say a 2 by 2 vector added to another 2 by 2 vector, you're good. The scalar multiple exists in the space. So again, if you take a 2 by 2 vector, you multiply by any real scalar, it's in the space of 2 by 2 vectors. That's where that comes from. The commutative property of addition, you can switch the order of addition and you get the same value. The associative property, if you add 3 vectors together, then it doesn't matter whether you add the first 2 and then the third one, or whether you add the second 2 and then the first one. There is a 0 in the space, and if you add it to a vector, then it's the same as the original vector. Adding a vector to its opposite, so by distributing a negative sign through it, you get the 0 vector. A scalar multiple distributes, so the scalar will be equivalent to multiplying the first one and then multiplying the second one before you add, or you can add first and then scale the result. You can also have a distributive property with scalars. So I can add the 2 scalars together and then multiply by my vector, or I can distribute the scalar to a copy of the vector and my second scalar to a copy of the vector and then do the addition. And same thing for multiplication. I can scale a scaled vector, or I can multiply the 2 scalars together and then get the vector multiplied by the vector. And if I multiply a vector by the identity scalar 1, then I get the original vector back. Now, any class of objects that satisfies these will also be considered a vector space. So just as an example, if I think about properties of functions, if I take any 2 functions and I add them together, I get another function. And if I scale a function, I get another function. If I add 2 functions together, it doesn't matter what order I add them together in, I get another function, and it's the same function. The associative property also applies. There is a 0 function, which is just 0. And if I add that to a function, I get the function back. I can put a minus sign through a function, and if I add it to the original function, everything cancels out, and I get 0. The distributive property in all of these forms applies to functions. And if I multiply a function by 1, I get the function back. So again, even though we don't think of functions as vectors in this context in linear algebra, because it satisfies all of these same properties, we can talk about functions in a vector space or function spaces. And we will see some of that as we go through some of our examples. So if you want to establish that something is a vector space broadly, then you need to prove all 10 of these properties. However, when we only want to test to see if we know that something is a subset of a vector space, then is the subset itself acting internally as a vector space? Some of these other properties we actually get for free. What we have to test are just 3 properties. So we have to test that 0 is a vector in the space. all these properties up here that had 0 in them, they won't apply if 0 is not in the space. We have to prove that if I add 2 objects in the subspace, I get another element in the same set. So this is called closed under addition. And I also need to be able to scale any object in the space with a real scalar and still get an object in the space. So that's called closed under scalar multiplication. And so if I can prove that these 3 properties are true, then, and I know that it's a subset of another vector space, then my subset will also be a subspace. So it will internally behave like a vector space. All right, so let's consider an example. So here I have my subset defined as the vector of the form ABC. And the restriction that I have on this set is not that A, B, and C can be any real number, but that A plus B plus C have together equal 0. So this is a subset of R3. So we know that R3 is a vector space. So we don't have to check all 11 conditions. We just have to check 3 conditions. So the first condition is 0 in the set. Well, if I let 0, 0, 0 for my vector, I need to check, does 0 plus 0 plus 0 equal 0? And the answer is yes. So 0 is in the space. What happens if I add 2 elements together that are in the space? So let's say I have ABC that's in W, and I also have DEF that's in W. Now the requirement here is that if I add up all of these elements together, I get 0. And therefore, if I add up all of these elements together, I also get 0. If I add these 2 vectors together, I get this vector. And if I add these 2 equations together, I get this expression. Rearranging them is equivalent to this expression. So does A plus D plus B plus E plus C plus F equals 0? Well, yes, because if I collect all my ABCs and all my DEFs, A plus B plus C is 0, and D plus E plus F is 0, and therefore 0 plus 0 is 0. So the sum of these will also still add to 0. So that's test 2. And then the third one is if I multiply a vector in W by a real scalar, say K times ABC, well, does that add to 0? Well, KA plus KB plus KC, I factor out the K, A plus B plus C, I know is already 0 by the definition of W. K times 0 is 0. So this satisfies all of the conditions that I have to check. So the set W is a subspace of R3. Now let's look at an example where it's not a subspace. So here I have a set H, which is given by a 2 by 2, a 2-dimensional vector, A and B squared, where A and B are free to be real. So this is a subset of R2, but is it a subspace? Now, if H is not a subspace, we only need to show that one of the conditions fails. We don't need to show that they all fail, only that one of them fails. So sometimes finding a counterexample can be somewhat problematic. But again, you generally only need one example to fail. Now, when you have a squared like this, it's often useful to look for negatives because that's where the behavior is going to be different. So essentially, this set that we have where we have A and B squared is equivalent to another definition of the same set where we have X and Y, where X is real. The first component can be anything we want, but the second component can only be greater than or equal to 0 because we have B squared. And if you square a real number, then you can only get 0 or bigger. So let's consider scalar multiplication. So if we consider the element 1, 4, which is in H, and multiply it by the real scalar -1, we get -1, -4. But this is not in H because b squared equals -4 does not have a b value that can be real. There's no real H that can make no real b that can make this true. So therefore, we have to conclude that this is not closed under scalar multiplication, and therefore H is not a subspace. Now, in addition to traditional vectors from Rn, we can also have other types of things which are also vector-like. So we can include matrices, for instance. We can also, because we're not doing matrix multiplication, we're doing addition and scalar multiplication. And that just is component by component. And it's relatively easy to see why this would be a vector space. We can represent it, we can actually think of it as essentially a vector in R4, A, B, C, D. We can also do polynomials this way. So these would also be treated as if they are vectors. Again, if you add two polynomials together, you add them component by component. You add the constant parts, you add the linear parts, you add the square parts, you add the cube parts, etc. So again, this would be equivalent to representing a four-dimensional vector in a P3 example like this. So any set that is isomorphic and essentially behaves similarly to a vector space will itself be a vector space. And so then again, we're left with, if we have a subset of that space, can we determine if it's a subspace or not? So consider the set of 2 by 2 matrices, A, B, C, 0, where A, B, C are real. Is this a subspace? Again, we're assuming that all 2 by 2 matrices with all real components are, in fact, a vector space. So then we just have these three conditions to check. So if we set A, B, and C equal to 0, we get this, which is the 0 vector in this set. If you add it to another vector in the set, you get the original vector back. So that's fine. This bottom entry is still 0. You're good. Consider the vector or the matrix, in this case, A, B, C, 0, and the second matrix, D, E, F, 0. What is their sum? Well, it's this. But all three of these entries, again, think about these positions here as the value of the A1 position, the value of the A2 position, the value of the A21 position. These are all real, so it satisfies this definition, and therefore the set is closed under addition. Likewise, if I take a scalar and I multiply by my U matrix, I get Ka, Kb, Kc. As long as K is real, then these will also be real, and that'll satisfy our definition. So this meets all of the requirements. So this set M is also a subspace. Let's consider the set of polynomials of degree 3 or less. So that would be P3. This is a subspace of Pn. Pn is a vector space. Again, basically you add things component by component. So it satisfies all of our 10 properties. So the question is, does P3 constitute a subspace of Pn? Well, is the vector in the set? Well, we could set all these coefficients equal to 0. That would be 0, and that is in the set. Is the set closed under addition? Well, if I add two polynomials that are both degree 3 or less, and I add them together, the resulting polynomial is also going to be degree 3 or less. So here's a dummy polynomial, a plus bt plus ct squared plus dt cubed. And my second example, e plus ft plus gt squared plus ht cubed. And if I add them together, then I add the constants, a plus e, that's still real, b plus f times t, that's still real, c plus g times t squared, that's still real, d plus h times t cubed, that's still real. So it is closed under addition. And finally, if I check scalar multiplication, if I multiply a polynomial by a constant, a real constant, then k times e, that's still real. K times g for t squared, that's still real. K times f, that's still real. K times h, they were both real before, they're both real now. So all of the coefficients are still real, and therefore it is closed under scalar multiplication. Now, it is worth noting that P3 is a different set than the set of all polynomials that are exactly degree 3, because in exactly degree 3 set, you would force that last coefficient, A3, to be non-zero. So in this case, degree 3 or less, you can allow A3 to be 0. But if it says they're exactly degree 3, that would not allow the 0 would not be in the set, because you could not get rid of that t cubed term. So you have to read these descriptions very carefully, because they matter a great deal in terms of what is and is not in the set, especially if they do the description in words rather than by listing out an example element. Now, another example that's a little bit more abstract would be, consider the set N of all functions that are neither even nor odd. Is this a subspace of the set of all functions? Recall that even functions are functions such that f of x is equal to f of negative x, like x squared, absolute value of x, x plus x to the fourth, etc., cosine x. And odd functions are functions such that f of negative x is negative f of x, like x, x cubed, 1 over x, sine x, etc. Functions which are neither even nor odd may be composed of combinations of odd and even terms, or may contain terms that themselves are neither even nor odd, like e to the x, square root of x, log x, etc. Now, as it turns out, this is not a subspace, and it fails actually under 2 reasons. So does n contain the 0 function? So if f of x equals 0 is in this set, it has to be neither even nor odd. However, that's actually not the case, because f of x equals 0 is both even and odd. So it is definitely an even function. F of negative x is still 0. And also negative f of x is also still 0. So it is actually both even and odd. And so it's not in the set. This also fails the addition test. So if you add a function like 3 minus x together and x plus x squared together, these functions are both in n in our set. But if you add them together, the x elements are going to cancel out, and you end up with an even function, which is, if it's even, it's not a neither type function, and therefore it's not in the set. And so this fails under the addition test. It's not closed under addition as well. So this is not a subspace. And then our last example, we're going to consider F the set with elements of all infinite series with a finite sum. So the infinite sum from I equals 0 to infinity of a sub I, and it has a finite sum, so it's equal to L of some sort. Is this subspace of the set of all, is this a subspace of the set of all infinite series? So infinite series would be a vector space under this assumption. And so we want to test our 3 conditions to see if it satisfies our subspace properties. So is the 0 element in the set? Well, yes, because if I'm adding up zeros, my limit is going to be 0. So yeah, that's fine. That is a finite limit. So it does act like the additive identity should. If I take any 2 elements in the set and add them together, are they also in the set? So is it closed under addition? So let's say I have two infinite series that have finite limits, and I add them together. I can add them component by component, but I also know that if the sum of a sub I is L and the sum of B sub I is M, again, different potentially finite values, then when I add these up, I still get L plus M. And if these are both finite, then the sum is also finite. So yes, the sum is in the set. And what about scalar multiplication? Again, yes, as long as K is a real value, I just multiply it by every term in the sum, and the limit will then be the sum. The finite sum will just be K times that finite limit. And as long as K is a real scalar and L is finite, then their product will also be finite. So F would also be considered a subspace. Now, the most common error that I see with students checking these, quote unquote, checking these conditions is going through the motions and not actually thinking about what they're writing. So they write down the three things and they say, oh yeah, it's fine. Oh yeah, it's fine. Oh yeah, it's fine, without stopping to think about whether that's actually true. So again, don't get too hung up on the notation, especially for abstract cases, because you do actually have to think about, is this actually valid? And again, sort of processing what the conditions mean, because again, they're not always going to work out. We've seen some examples where they're just not true. And if you just go through the motions, you might think, oh, well, it's just always true, and they're not always true. So again, it's important to actually like verify that in fact it is in fact true or is not in fact true. Simply writing down the notation repeatedly is not the procedure. Just because you can express a thing in notation doesn't mean that it's actually true. So again, you need to apply your logic to make sure that you're actually checking and thinking and not just copying a sort of style.